I used to wear contacts more when I was in Michigan, but then the pandemic hit, and I stopped wearing contacts.
Are we ready to go? Okay. Welcome to our discussion today. Today, since we start our forecast contest, the National Forecast Contest on Monday, our forecast Sarina, Luo Chen, she's running the whole thing, and it's not a small deal. So she's going to tell us a little bit about how to go about that. So it'll take the first few minutes of our discussion. Okay, and then we're going to get into some weather.
Yeah, so the forecast city for next Monday has been released. It's going to be Fort Myers in Florida, in the southwest Florida. And you can see on the weather challenge schedule that the climatology here is with a low of 75 and high of 91 climatologically. And the wind speed is going to be 12 knots and an average precipitation of 0.21 inches at that location. And we can look where it is on Google Map. So here's our forecast location, and if you pay attention to the National Hurricane Center, you know there's going to be a huge storm there. So the wind and the precipitation forecast is going to be harsh. Yeah. So what we're going to do first is if you have no idea about forecasting, I would recommend to go to the GFS MOS. And the forecasting period we're going to do is from 60 to 60, so this period, and the submission end time is going to be about 0Z, so which is 7 p.m. At the prior day. So going from the top to bottom, what is showing here is the minimum and maximum temperature for the date, and temperature at the second row, dew point temperature, cloud cover, wind direction, and wind speed. So the maximum for tomorrow at Fort Myers is going to be about 8 knots. Precipitation, probability, and quantitative. So that's the thing that we're going to use mostly. And if you don't know what details are, you can go to the website that explains what it is. MAD. Here, we'll go there. Open it up. So, and there's other tools that I want to show you. It's called Windy, and you just pull up the location, and it kind of gives you the comparison between different models. GFS, EC, Icon, Meteo Blue, and NAM, even HER. And there's also a LAMP website. You can pull up the location by typing the forecast station here and compare the LAMP ensemble or statistical forecast for the location with the observation. Sorry, it takes a while to load up. Oh, never mind. So we can enter here and see what we actually gonna put into the forecast contest. So we can we're gonna go to submit forecast and put your forecast ID and password here and select the school to University of Wisconsin-Madison. And if we gonna believe the MOS data, so not for the forecast time, but if we're gonna put 76 to 90 for the highest and lowest temperature, and the winds, just pick anything 12 and 22. And then that's gonna be your first entry for the forecast. You can choose the guidance forecast. If you forget to predict for the first time, you get a pass of using the guidance forecast, but the second day wouldn't count. So just save that and you can submit your forecast once you enter everything. And the forecast time is Monday, Tuesday, Wednesday, Thursday, and we're gonna forecast for Tuesday, Wednesday, Thursday, and Friday. So 4 days a week. Just remember that. And since we are talking talking about the Florida, we can look at the ensemble here. Here. So this perturbation is going to be, yeah, it's going to be hard since our forecast station is right here, and the investigation is probably going to be become Hurricane Hermine, and it's brewing here. If we're gonna look at the satellite later, and most weather station or ensemble member agrees it's going to curve to the Florida and bring a lot of rains and winds there. Yeah, this is the forecasting cone here. It's going to intensify into hurricane pretty soon, and so the Tuesday forecast is going to be tricky since we're forecasting for Wednesday. Yeah. If anyone, I guess John's going to discuss about this later.
Just a little.
Yeah, sure. Yeah, so I've done my job here, and John is going to.
All right.
Thanks. Do you have a website with all these links you've been showing, or do you want to have a web page that people can access them from?
I do. I have that on the AOS,
Okay.
GSA
Sounds good.
website. Just the links that I usually use here.
Perfect.
Yeah.
Oh, great. Okay.
Yeah,
That's
so
great.
it's aos.wisc.edu/tilde/GSA/weather challenge, and you can have, I will update the station, so the links to the station every 2 weeks, just so it makes everyone's life easier.
Great. Thanks very much, Noel, and thank you for taking on this challenge of organizing this.
Don't forget
It's
to
really
forecast.
helpful. Okay, we're getting our machines to come up in a minute. A lot of interesting things going on, of course, today and into the weekend. We will talk about Fiona and how the extratropics come to the rescue and take what's kind of a ragged, no, it's not a ragged hurricane, it's a really intense hurricane, but the combination of the hurricane and the extratropical dynamics that are also strong in this case will really drive this thing into record territory. So Maritime Canada is going to be hit by the worst storm it's ever seen, and the whole country of Canada will thereby get the worst storm it's ever seen. So we'll talk quite a bit about that. There's also, as Noel points out, there's a new hurricane brewing that will directly impact finally the United States for the first time this year. And there'll be some interesting contrast to make between that storm, and it's all a forecast now, and Fiona's real, but the contrast between how that storm and its interaction with the extratropics behaves, at least in the forecast, as compared to Fiona. So that'll be kind of an interesting thing to talk about. Some of the rest of the discussion will be somewhat abbreviated than from our normal routine, simply because there's all sorts of interesting things to talk about and we don't want to put them off. So let's start first, Pete, with the satellite movie, as we always do. Get a nice view of what's going on around the continental 48 and adjacent waters. And there's Fiona spinning away furiously. Bermuda's right around in this location. I think it's past Bermuda now, but it's I don't know its intensity at the current moment, but I think it was probably going to be about in Category 3 range, but it certainly has spent some time, may still be in Category 4 range. So it's a very intense Atlantic hurricane, and it's racing northward. There's Bermuda, sorry, there it is. And it's racing northward as the storm rages on. And look at this low-level stratocumulus off the coast of the northeastern United States. It looks almost like December or January, doesn't it? This is really cold air. So I don't have to tell you that. Last night, the temperature got down into the 40s. It'll probably be low 40s tonight. Well, maybe not because of this thing invading, but low dew points, really chilly temperatures for the first time all year, and it's in great contrast to what we had Monday and Tuesday, where I think we had a dew point on Tuesday afternoon in the high 60s. I believe it was 68 after the deluge that we had around 2 p.m. Dew point rose back up to 68. And then yesterday afternoon it was 41. So a tremendous air mass change, and that's not of no consequence for what happens to Fiona, as it turns out, and I'll show you that. This baroclinic zone that's kind of come through and cooled everything down in the eastern United States after some pretty heavy rains yesterday, that is the baroclinic zone with which Fiona will interact and turn into this massive storm that is going to ravage Nova Scotia and Sable Island. So it's going to be really wild there, all of Maritime Canada, actually. So that's the feature of greatest interest. Here is the new investigation area that looks a little better today than it did yesterday. I think Isaac in our class was talking about it. It was hard to see from a distance any rotation. There still is a disjuncture in the vertical, I think, between the rotation, which is back here in the lower clouds, and the convection that's kind of leading it a little bit ahead. So I don't really know enough about hurricanes to say whether that is the recipe for disaster for the storm or whether that's kind of the way they begin their lives. So go ahead.
Yeah, they're calling it a tropical depression now, and some concerning forecasts for the western Florida peninsula as well.
I mean, this is how Fiona looked in its early stages, as if the shear was in the opposite direction.
Oh, is that right?
More easterly shear. But like, I think the main concern of the National Hurricane Center is that shear is gonna abate soon, because so a lot of that shear was actually from the outflow of Fiona, and Fiona's like racing away.
Oh, yeah, okay.
So as it races away, there's gonna be less shear. It's just more.
So they get themselves a little
yeah.
bit
So
vertically
yeah.
aligned.
So it's gonna vertically align.
And then the warmest waters in the hemisphere are right about here. And that's where it looks like over the next day or two, maybe 3, it's headed into the southern Gulf of Mexico, straight to Florida. That's really warm water. So bad news for likely continued development. What is it going to be called, Noel? Hermine? Hurricane Hermine. It's kind of nice.
There's a depression in the Cape Verde that's
is that
racing
right?
with it.
Yeah.
So it could be, it might not be H, it could be I.
Yeah.
Ian, I think, is high.
Yeah, so all of a sudden the season seems to have picked up the pace, and it's now a couple of weeks past the peak. But you know, there have been years where October is the worst year of the hurricane season, so that's not unusual.
And I think that's common in La Nina years.
Oh, is that right?
More common in La Nina years, yeah.
So here's the disturbance that will pretty much plague us all weekend long, although it makes for a really nice afternoon right now. As you can see, the leaves on the trees, some of the species are already turning yellow, so there's a nice burst of initial color with a gray sky that always brings the contrast out more, and that gray sky is going to be around much of this weekend. Intermittent rain tomorrow, we may get to that forecast, and then more prevalent rain, I think, on Sunday, especially morning. So not a great weekend, but not a terrible weekend. Much better than the one they're going to feel in Maritime Canada. So that's all we can see on this satellite movie for now. Let's go to the radar, the national radar, Pete, get an idea of what's happening around the country. So you can see this is moving in relatively quickly, and will be raining here this afternoon, almost surely. And this thing is still getting itself organized. One can almost see a center of rotation over northeastern North Dakota, perhaps, as some of these cells move over this very short 6-hour time. So that's the weather system on our doorstep. We'll pay a little bit of attention to that. Unfortunately, we pay more if it were not for Fiona. And then you can barely see the edge of Fiona. Some of the showers on the far western periphery of the complex now between Fiona and the extratropical storm in far western Nova Scotia, Bay of Fundy area into New Brunswick. Okay, and let's go to some upper level charts to set the stage. We'll skip the surface map today just for time. So here's our 500 millibar map from this morning at 7 a.m. So there's the signature at 500 millibars of Fiona. Here's the signature of the upper trough that is making its way toward Fiona. Now, don't be confused that this thing looks kind of wimpy. It looks a little bit wimpier today than it did yesterday, but look at right here. This is minus 20, it's minus 21 at Islip, New York. Minus 20 isotherms analyzed all the way down off the New Jersey coast. This is minus 10. This is a substantial upper level horizontal temperature contrast. And I'm gonna, in a minute, show some of the evolution of this, and in Vis 5D we'll see it even more clearly. This is a really strong upper level front, as it turns out. And unusually strong for this time of year, in my opinion. And not only is their baroclinicity large, but the way these things form forces there to be a really strong vortex signature there as well. Not just from the curvature, but from the windshield. Look at this, 25 knots at Islip, 90 knots at Wallops Island. There's enormous horizontal shear in this region, and that's not by accident. That's a function of the way that this baroclinic zone developed. So this thing is quite distinct from the cold front at the surface that went through yesterday and over the eastern coast, eastern United States yesterday. This is quite distinct from that. And so we'll have to say a little bit more about that. But it's the marriage of these two, or at least their close proximity, that makes it really interesting. Later on, I'll show you a cross-section roughly at this time. Actually, it'll be at 15Z from an old forecast. It cuts right through the location where the upper baroclinic zone is closest to the core of still tropical Fiona. We'll be able to show that in just a minute. And that cross-section will show this feature has deep frontogenetic activity along it, which forces a strong band of ascent. Fiona still has its own tropical ascent going on. They get close together, and trajectories of air go to the tropopause immediately. There's almost no time there, and that's when the sea level pressure starts to drop like a rock. So it's a beautiful illustration of how this interaction is going on. I'll show you that in just a minute. And here's the upper trough associated with the cloud mass that's over the western Great Lakes states and the plains, high plains, and that's the feature that's going to ruin our weekend, it looks like. And very often when this ridge crest moves by, and it already has, that's when the clouds come in, just as a kind of rule of thumb on these things. And so this morning, the sky wasn't particularly full of clouds at 7 a.m., but this has now progressed to the east, and so the ascent is a function of divergence with the supergeostrophy here, subgeostrophy here, and the divergence is just upstream of the ridge crest. And so that's where the clouds are coming from. Okay, I think that's enough for there, Pete. Let's go to 850 just to see what Fiona looks like there in the analysis. And there's Fiona, and it's a region of high temperature. The high is like 21.8 degrees C in the middle, but it doesn't have that, on this type of analysis, it doesn't really show that beautiful warm core, but it has it. And we'll see that from a number of different perspectives. Here's the baroclinic zone that has ushered in our really nice change in the weather and made it all the way off the east coast. And so at 850, Fiona is really close to that trailing baroclinic zone. That's trailing from a cyclone that's now kind of weakened a little bit, but it's now up in the Labrador Sea. It was a little bit stronger yesterday. And then here's the ridge and the upstream ridge, and in this location is where the anticyclone is. The weather is really nice. You saw that on satellite. More cyclones brewing in western and archipelago of Canada. Some of that's lee side troughing. This geopotential height, minimum at 850, is coincident with a maximum in the isotherms. So that's a lee side trough, and that feature will have an impact also on our weather this weekend. It's part of the circulation that's evolving as it comes off the mountains, but it's supported by an upper level wave. And then there's this other one way up north in the Yukon and Northwest Territories that's just a cold low, and that one's supported by features at upper levels. We'll see a little bit of that when we go to the forecast. Okay. I think let's go to Fiona a little bit more closely if we can. Let's one more thing, Pete. 300 millibar jet and then 250. We want to just see that. So here's Fiona, and there's the jet at 300 millibars, 148 knots, and this is in, sitting on top of the baroclinic zone associated with the storm that's over the Labrador Sea. Let's see it at 200 millibars. Go a little bit higher and see what that looks like. And there you see there's kind of an extension southward of the jet to where there's still a warm core at 200 millibars. I mean, this is a deep storm. And my conjecture is that this is outflow from Fiona that is tilting the tropopause right at the height of the tropopause and intensifying the jet. These are the strongest wind speeds over maritime Canada are at 200 millibars. So this is a subtropical type jet that is kind of making its connection with the pre-existing, perhaps polar jet that was tied to the cyclone in the cold front that was there to begin with. So this is maybe one of the first manifestations of the interaction of Fiona with the extratropics, is the way that it's, I think, modifying the jet. It's 150 knots here at Halifax, maybe more than that, 153, I guess. So that's an observation at 200 millibars. That's a strong wind. And then we've got this feature downstream of the ridge axis, this sort of stubby ridge axis, pretty strong upper level jet itself. And that is why I'm confident, and I'll show you this in Vis 5D, why I'm confident this is really a strong mid-latitude impulse that's going to get itself right close to and interact with Fiona. Where this weaker, I think this might be a whole different complex for the weekend for maritime Canada. But the upstream feature is stronger and independently stronger in this instance. It doesn't have anything to do with Fiona, but it's soon going to. But that's not the case quite yet. Okay, what do we want to do next, Pete? I want to show you some, can we look at the quasi-geostrophic omega? This is really interesting. We'll focus on just one time. And I'm showing you in a slide back up to the top of the page, because I'm using the old forecast only because I want to have the old analysis. I want to be able to show what these features look like separately and then how they come together. I'll do the same with Vis 5D. Let's take a look at the total omega field at 700 millibars at forecast hour 12. Initiated, wait a minute, is this? Yeah, this is right. Okay, so this is 12 hours valid on 12Z this morning. So it was made last night at 0Z, just what I hoped for. Great. So 700 millibar omega, it's quasi-dystrophic omega. The blue is subsidence, every decipascal per second, which is about a microwatt per second. Yellow is ascent. So you can see right away, there's Fiona. And, we're not trying to resolve the vertical motion from Fiona this way, but it's got a vortex structure, it's got some thermal structure, it's going to show up in the QG. The more important thing for the QG is this subsidence right here. Okay, you'll see that as we go on.
Quick question, does the QG omega that's shown here, does it include the diabatic heating terms?
No, there's no diabatic heating.
Just the adiabatic terms?
No, just adiabatic terms.
Okay.
So it's just the Q vector convergence and then you invert
Okay.
that, so no diabatic terms. Good question. Okay, let's go to 24 hours, Pete. And things are very different. So this is tomorrow, this is tonight. Things get very different very quickly. So this is the strong ascent associated with whatever Fiona becomes during the day today. It's still tropical, you'll see in this 5D, but it's got an extra tropical vertical motion couplet here. This is extraordinary. This is a 22 meters per, not meters, about 22 centimeters per second, synoptic scale updraft. And that's it's greatly underestimated. And then there's this hook of strong subsidence, especially strong on the south side of the storm. So how does that happen is part of what you want to know when you're talking about one of these extratropical conversions. But that much mass being lifted, this is just a 700 millibar testimony, but the whole column is being lifted and the mass of the whole column goes down and the pressure falls rapidly when that happens. So you'd like to understand why that's going on. Okay, the best time though is 30 hours, and that's the last one that we'll look at, but then we'll do a sequence. This is the 30-hour forecast from last night of the vertical motion. So even more intense. And look at where this is. You can't even see the map anymore. This is Nova Scotia and Sable Islands. Right here to the east of Halifax is the maximum updraft. And then there's this extraordinary downdraft here. And the dotted lines are thickness from 500 to 900 millibars. So there's the coldest, lowest thickness. And the warmest air is right in here. It's like an occluded structure with intense vertical motion in the occluded quadrant, even though it's not really occluded. But that's what it looks like. So now let's do this, Pete. Let's take a look at pieces of this. So that's the total quasi-geostrophic omega. No approximations except we drop the diabatic terms. Now let's look at the part of that comes about from the long isentrope Q vector convergence. And so you get the two big lobes, but you don't get the connecting tissue in here. But the same strong vertical motions there, ascent near Halifax and descent back here. And this is valid tonight, midnight. Let's take the next piece is the transverse omega. What is the part that's coming from the across isentrope Q vector? This tells you something about the vertical motion associated with the fronts or frontal structures, baroclinic structures. Boy, is that strong. And once again, Nova Scotia, Sable Island, it's sort of central Nova Scotia where the ascent's really strong. But look at this beautiful yin-yang structure. This is like the warm front and into the occluded portion, and this is all the subsidence behind the cold front. And it really shows up. This surprised me, that this storm, only a day into its conversion, has such a characteristic extratropical frontal vertical motion structure. But I don't think it's because the fronts are well formed. I think that's not the reason. But anyway, it's a beautiful structure and really intense vertical motion. Then you can do one more thing, which is fun. You can say, what if we're back in 1947 and all you have available is positive or negative vorticity advection by the thermal wind, the Sutcliffe development theorem. That's in this portion of the omega equation. So here we completely neglect the deformation terms that are part of it, and this is what the Sutcliffe-Trenberth formulation looks like. And that looks exactly like the long isentrope Q vector convergence, which you can theoretically show why that's the case. Very strong ascent, very strong descent. But that's just vorticity advection by the thermal wind. The vorticity can be split into shear and curvature, so let's see what that looks like. Let's see what that split looks like. So here's the shear vorticity advection. Compact little ascent region right over central Nova Scotia. It's not got the big scale. You can even see a little bit more of the thickness, thermal contrast underneath it. But it's still pretty intense. Now let's do the curvature vorticity, which is the next piece. Bigger scale and bigger magnitude. So at this time in the development of this extratropical conversion, it appears to me that the curvature vorticity is dominating the development phase by pumping mass out of the column where the ascent is really strong. I don't know what that means in the broader context of how these things generally behave. I still don't. I've been saying that for years in this forum, but I still don't understand it yet. I'm still working on it. But it's But it's interesting to look at the partition. One last piece, what about these so-called neglected deformation terms? We'll hear about these in 452 soon. Look what they look like at 30 hours. Wow. If all you do is look at the thermal wind advection by the vorticity, you're neglecting all of this extraordinary vertical motion. It's not going to show up in your formulation, and all of the substance on the backside. Extraordinary strength, and in roughly the right place. This is now between Nova Scotia and Newfoundland, so it's a little bit off to the east of the main development area at this time, but nonetheless, a large swath of really substantial synoptic scale vertical motion would be completely out of your analysis if you do not include the deformation term. So this is a good argument for using the Q-vector form of the omega equation. And this looks better as time goes on, but we may not be able to show it. Oh, we'll do it one time. I got to show you this. At forecast hour 42, which will be valid midday tomorrow, let's take a look at first the total, just so you get an idea of how these all work. So here's the total vertical motion. The whole thing kind of falls apart during the day tomorrow in terms of the quasi-geostrophic forcing. But there remains here at the mouth of the St. Lawrence River a really strong ascent region, okay? And so I wonder what's composing that ascent region. Let's take a look at the what do I have down here? Yeah, the shear-wise vertical motion at that time. It's pretty big. Okay. Is that what I wanted to do? Yeah. And then, no, I didn't want to do that beat. Sorry. Let's do this instead. Sutcliffe Trendworth at 42 hours. That's what I meant to compare. Not very big. Okay. Over Labrador. And what about the deformation? That's what's driving the total quasi-geostrophic vertical motion. So again, watch out using the old approximations. They're interesting and they're really foundational for the development of the ideas surrounding how we can diagnose vertical motions in the mid-latitudes. But you got to be careful to not succumb to those temptations to get rid of terms that are second order and look kind of small, and you can argue in their way. Reggie Sutcliffe went to his grave, and I have proof of this, went to his grave believing that the deformation terms were negligible. And I have a letter from Hugh Davies from 1978, where they were corresponding, not 1978, 1983, where they were corresponding about that. Son of a gun. And Hugh wrote me a letter when I wrote this paper years ago about the importance of the deformation terms. He says, Sutcliffe would have loved to have seen this. He went to his grave thinking that he was right about the other thing. So that was really cool. I have that saved. Okay, so it's a great illustration of that today. Okay. Let's go to Vis 5 DP, if there's no questions or comments. Okay, so what we've been talking about up till now is thinking about how are we getting the air out of the column in which Fiona at the bottom of it is supposed to get really intense. So we're going to look at this from a forecast perspective. This is from the GFS initialized at 6Z yesterday. So I know that's old. I know that's old. But again, the reason is because, number one, the forecast doesn't look fundamentally different today. And number two, I don't have to start with an arbitrary time where these things are already close together. So this is, I can see how they evolve in their interaction by looking at an older forecast. Luckily, the old forecast is quite like the current one. So that saves us. So here's sea level isobars every 4 millibars, but everything only lower than 1,000 millibars. So there's Fiona at 6Z Thursday. And here is the cyclone that brought us our change in the weather, and the cold front trailing from it is the thing that brought us cooler and drier air. And it hadn't yet gone across the East Coast. It was raining yesterday heavily in Boston and in New York City and Portland, Maine, because that was in dew points were in the 60s and 70s. And so that's changed now. So let's just march through this a little bit. This is every 3 hours from the GFS. And so you can see that cyclone up in Labrador is kind of spinning away, and here's the cold frontal trough associated with it. And then here is, oh, I want to get those trajectories off. That's giving away the, yeah, sorry. Thanks, Pete. Okay, and here's Fiona. It's pretty intense. This is a 996 to 988, so it's not a weak storm. Keeps on going. And then suddenly, something changes. And we're going to see blue isobars that are below 980 and lower. They start to show up. Watch this. Look at that. I mean, what's going on there? Rapid development. And this is now 980, 76, 72, 68 in the GFS as resolved by the conversion to Vis 5D format. It's actually lower than that. And here's Nova Scotia, Sable Island. So it's just about there, and this is now midnight tonight. So roughly what we were looking at the 30-hour forecast. And so that's a really intense cyclone. Our original one remains but now this thing has really taken up residence, as it turns out, along that baroclinic zone. So let's go back to the initial time, if we could, Pete. And then let's put 500 millibars theta on top of there. I think it's just that one. Yes. This is theta at 500 millibars. Now, the reason I'm showing you the 500 millibar theta is because I want to show you where this upper level frontal disturbance is. So once again, here's Fiona. Look at how it's a warm core disturbance even at 500 millibars, intensely warm core. And then here's our sea level isobars, but these are now 500 millibar isotropes. And so the front has a pretty steep slope because it's even existing right just about in the trough. It's a little bit back behind the trough at 500. But look at over our region yesterday evening. We have this really intense 500 millibar horizontal temperature contrast. Click through a couple of times. Let's go to the fourth time, I think, in particular. Right there. And at that time, you've got a really intense baroclinic zone through southern Michigan at 500 millibars. And then this Fiona far away, and still a warm core disturbance, just kind of looking around, wondering what to do. So let's take a look at a vertical cross-section of theta. I think this one is at that time, yep. So that's what theta looks like in the vertical, if you could tilt it up for us, Pete. So that 500 millibar level vertical horizontal temperature contrast has deep continuity, comes all the way from the tropopause down. And so here's your mid-latitude tropopause, here's maybe your tropical tropopause. There isn't much of a step between them, it's just a really deep structure there. Let's see what the potential vorticity looks like. Oh, first, top level, let's put the regular vorticity on there, QZ in the horizontal. So there's 500 millibar vorticity. See the lines, they get a little garish, don't they? Maybe we can take the theta off just for a second. So here's a strip of really intense 500 millibar vorticity. It's right where it should be. We've got a cyclone here and then a cold front trailing through the trough at the surface. Notice the frontal vorticity is displaced to the north at 500 millibars, just as it should be. Intense vorticity, even at 500 millibars with Fiona. But look at this feature right across, this, draped across our state into Lake Michigan. That's a really intense upper vortex. And so let's take a look at the PV along this cross-section, Pete. I think I have PV, not PV. And then you can tilt it up.
Do you want theta on there also?
Yeah, I think we can see both of them. Let's see if it works. I think you can see that. Yeah, so this is the theta's in green, of course, and the potential vorticity, contour to every PV unit, 1, 2, 3, is in purple. And it's an extraordinary depression in the PV. These surfaces here are at like 5.4 kilometers, so this is down to 5 kilometers above sea level, and originating from way up here at the tropical tropopause. So so that's kind of setting the stage. That's what the structure upstream looks like. There's a really potent upper feature, and purely mid-latitude, and independent of what's going on in the tropics. That thing is poised to meet with Fiona in this instance. Okay? So let's go to the top view again. We'll take the PV cross-section off, and this time we'll put omega on there. And I'm only showing the regions where the air is sinking. So how do you get these strong upper baroclinic zones, these strong vortex structures? Let's tilt this up. Look at that. It's unbelievable, isn't it? And this is September 23rd that this is happening. This is a midwinter, best of the winter type upper front situation. This is, the outer contour is 2.5 centimeters per second. I don't know how many there are in there. It looks like 4, maybe 8, 12. Something like, what, 30 centimeter per second downdraft at the core of that, which is extraordinary. And then put the PV back on, Pete. And that's how you're dragging this PV down these sloping isotropes. It's coming right out of the stratosphere, filling the lower almost lower troposphere, certainly mid-troposphere. And this is a classic upper level frontal system. And we had a beautiful day yesterday. Clear skies, the whole thing. You see, you don't even notice it. They stealthily progress over your head, and yet they're winding the spring for downstream development in a really substantial way. So this is an extraordinarily strong first day of autumn upper level front that is poised to make contact with a Category 4 hurricane at relatively high latitude in the Atlantic basin. This is an unusual set of circumstances. Okay? Let's go one more time to the top view, if you could, Pete. And then we'll take the vorticity off. Thank you. You're so good at this, Pete. Theta at 500. And then take the mean sea level pressure off and put pressure on there. So this is the 500 millibar. It's equivalent of the 500 millibar map. Geopotential is substituted for by pressure at a constant height level. And then isotropes. you might wonder, how do you get this kind of cone of extraordinary subsidence? And that's going to be favored in regions where there's geostrophic cold advection in cyclonic shear. So you can measure the cyclonic shear by eye by just seeing how tight the geopotential height gradient is here over Lake Michigan, how weak it is to the north, how weak it is to the south. So the cyclonic shear is over Michigan in the northern part of the lake, very strongly. And then follow any one of these green-white lines as a streamline of the geostrophic flow across the isotropes, and you see that this is cold air advection going on all the way through this region of strong shear. And so that combination, Sawyer and Eliason showed that that is a really strong mechanism for driving the air downward, as it turns out. It can be equally considered from the perspective of shear vorticity affected by the thermal wind. The thermal wind is really strong when you have a strong horizontal temperature contrast, and it's headed in the direction of the isotherms like that. And the shear vorticity is really all you need to make this explanation, even though curvature will add in the same way, but just on a bigger scale. So that's a really cool way to look at the way the upper front's developing there. But look at how far apart they are. This thing's over the Great Lakes, and we've got Fiona way over here. So let's march forward a little bit, Pete. We can take the cross sections off for the time being to kind of clutter things up. So let's just go forward, and remember this is every 3 hours. So here's the upper front. Looks a little better when you do it every 3 degrees, like you have control over in Vis 5D, than every 5 on the NSEP maps. Here's the Fiona. Keep on going. Okay, they're still pretty far apart. Keep on going. Oh man, this looks pretty interesting. That thing does not lose any vigor, and Fiona is now about half the distance away that it used to be. It's like, you know, holding in the first and 10. Here we go. Oh man, one more after that. Awesome. Look at that. Close together, the strong baroclinicity remains at 500 millibars. Here's the warm core of Fiona, and we just saw the first sprouting of the 980 millibar isobar. So it's going to really start to develop rapidly here. Let's take, go down to theta prime cross section. I think that's right through. Oh, I must have moved it. Can we slide it down? Oh, it's right there. You're right. That's the right time. You got the right time. Right there. So we want to see what this looks like. We should see a warm core and then a strong baroclinic zone. Let's tilt that up, see what it looks like. Oh man, that's what we see. Look at that. Look at that warm core. All the way to the tropopause, down to the ground, but intercepted about at 700 or so millibars by this baroclinic zone, which is the upper front we just saw developing. And then raced around the base of the trough, it's going to have a whole different vertical circulation associated with it by this time. But that's extraordinary. This is entirely extratropical. This is entirely tropical and remains steadfastly tropical at this time. There's no doubt about that. Let's put, I think I have a cross-section of PV on there. Yeah. There's the PV. Can you take those other horizontal sections off for the time being, Pete? Boy, do you see this. Here's the cigar-shaped PV feature that's characteristic of the tropical cyclone. You can't miss it. And then here's the upper front. And they are saying, hey, how are you? To each other. This is extraordinary in its anomalous nature. Okay, now take the PV off and let's put vertical motion on. No, not vertical motion. Sorry, Pete. I said the wrong thing. Frontogenesis, two-dimensional horizontal frontogenesis. So there's the action of the horizontal winds acting on the horizontal temperature gradient to produce a region where the gradient will be made stronger by that action. So this is the axis of horizontal frontogenesis associated with the upper front and the skirt of the tropical cyclone. There's a little bit of that goes on in the eye wall of the tropical cyclone too, it appears. I don't know much about that. But look at that axis. Now that is, in every single time I've ever seen it, that's going to be an axis across which there's a transverse circulation. Strong ascent on the warm side, if the frontogenesis is strong, and then descent on the cold side. And this is clearly the warm side. So now let's put omega on top of that. Oh man, look at that. There's a plume of vertical motion that I suspect is responding to the presence and action of this frontogenetic activity along the upper front, extending all the way into the lower troposphere. And then there's a separate plume of vertical motion that's just Fiona being Fiona. It's a tropical cyclone still. And then they overlap in the boundary layer. And if you want to make the pressure fall, you want to get the air out of the boundary layer fast. If you get it out at 100 millibars, it doesn't make much difference. The air isn't that massive on it in the same, vertical layer. But it's really massive when you're down here. And this air is being pumped out of the boundary layer upward and outward at an extraordinary rate. And it's a combination of this mid-latitude dynamics and the stubborn to give them away. Who would want to give them away? Tropical dynamics. And that's what's going to happen next when we go to the top view. Watch this. Just to remind you. Put the sea level pressure on again. And the other one too, yeah. So that's the first time we saw 980. Now we can go forward. Oh, keep on going. That is a lot of mass being evacuated out of that column rapidly. And destruction on Nova Scotia. Now, let's go back to the beginning. And I'll put the trajectories back on. We've got to see some of what the air is doing inside this storm. So I think number 2 is interesting. Number 7 is definitely interesting. And I think number 4 is interesting. So let's just see which ones are which. And then we'll get rid of that so we don't make any new ones. Take it back to slice mode or something. And then let's just animate this. Get a look at it first, and then we'll kind of pick it apart. Okay, so yellow comes in. We don't know what it does to the vertical yet. That's fine. We'll wait. Green comes in from the northwest over the Great Lakes, probably tied to the upper front. And then yellow, or orange, I'm sorry, comes in sort of on the southeast side of the developing system. So let's take a look at, let it animate to about 20 times in there or something like that. Perfect. Let's just tip it up, see what it looks like. Yeah, that's even better right there. Oh, man, I mean, that is something. And we can go backwards. Let's go backwards, looking at it from this view, a step at a time. So you can see here's air this is the stuff that came from the northwest over the Great Lakes. That's involved in the broad subsidence flow on the warm side of that upper baroclinic zone, helping to intensify that upper front, getting us ready for the extraordinary conjunction of the two that we saw in a minute. Here's air that kind of meanders its way towards Fiona and then just goes up in the convective updraft, or the eye wall circulation, most likely resolved as best it can be by the GFS. And then if we go ahead a couple more clicks, what's the orange doing? It's taking its time, but then it goes straight up when it hits there. And look at how fast it rises. It outdoes the yellow by a mile. That's the air that's just immediately exiting the boundary layer and lowering the pressure. In fact, if we go back a couple of clicks, maybe one more, right there is the time before the 3-hour increment where the air starts to rise in the orange trajectory. Let's see what it looks like from the top view and where the sea level pressure is. Oh, son of a gun, this is just when it starts to sprout. So the next time, we already know the orange has gone up. It continues to go up right in the core. Keep going. We know it's going straight up way beyond anything, and that's what's taking the mass out of the column. And this airstream has prepared the extratropical conditions that have led to this cooperation in the rapid development of Fiona. So there's a lot here, and it's a really, really interesting case. We're going to use this one in 452 because it has so many nice elements. It has a pre-existing cold front that's very much worthy of looking at the structure and all that. It's got an upper level front, which we'll learn about later on in the term, not that far away actually from now. It's got a really nice upper front, and then of course it's got a period of extraordinary development and dynamics along the fronts, which we'll talk about. So you can't beat it for a case. 2 Fridays in a row, we've been talking about these extratropical transitions. And they're really extraordinarily strong extratropical transitions, not just wimpy ones, run-of-the-mill. So, just been a great run here, and so. But I'm glad to say again, Michael maybe will watch this on video if he has a moment. Isn't it interesting how the extratropics come in to save the day? You've got a 1,000 or 988 millibar, hurricane category 4. This time I can't really say it. Category 4 is pretty good, but it gets even better. I mean, and that's because of the extratropics. But a great combination of the two. And let's look at the PV from the top view.
I'm gonna be the Greg of today and say this wouldn't be happening if the hurricane weren't there in the first place.
That's absolutely right. That's absolutely right. No, I mean, that is so true. So I'm kind of making a joke about the Michaels thing, but I do that just because I want to get under his skin. But it's absolutely right. If you had a category 1 and this is active like this, it's not going to be something that you're really that worried about on Nova Scotia. Category 4 plus strongest upper front I've ever seen in September, that's deadly. So let's look at the PV, because in the surface, sorry, isosurface. Oh, I had it saved that too. I guess, there it is, okay. So let's go back to the beginning and just animate that. Sorry if I got all the time. So here's the signature of the upper frontal feature, the mid-latitude feature. Really steep tropopause indicated by, I've colored it by pressure. So that's where the upper front is over the Great Lakes. And you don't even see Fiona on the tropopause yet. So let's keep going. And there's this upper feature coming in, and then you start to see a little bit of the effect of Fiona's presence there. And then they really get their act together right about here. And look at that extratropical. You can see right down to the surface from this 2 PVU surface. And then we flip up, Pete, we can get a nice look at this from this perspective. So we got to go back a couple of times because I want to show them separate first. Perfect. Look at that. So there's Fiona, the cigar-shaped PV tower, and here is the upper front that's coming in, and here's the air that's sinking on the warm side of it. If we go ahead a couple of times, just like last week, these two features kind of merge in the PV, and then the whole combined structure rotates. It looks like one of Lee's, tornado simulations slowed down, but it's not. It's on the synoptic scale. And so look at how this air is wrapping around and sinking to drive the tropopause down on the western side, southwestern side of the cyclone, and here's Fiona. If we can spin it around a little bit, you can kind of see how that structure looks all the way through. Just beautiful, isn't it? And you can't put that much PV at the surface and not have a cyclone below like 950 millibars. You just can't do it, especially over, well, now relatively cold water, but historically really warm water. That's a great picture. Look at that. How you get this ascent going right through the column, wrapping around descent, and then this straggly stuff right near the center of the storm originally finds its way finally, but it isn't, immediately obvious. So, what a storm. And I hope that the people in Nova Scotia are ready. I think they listen to their government in Canada more than we do here. Kalen, can you confirm that? He's not here. Too bad. Oh. Anyway, we have a little bit of trouble with that right now in our country. Hopefully we can get over that. But they don't have that in Canada. So I think the people on the coast are going to pay attention. And they're going to probably have taken all the precautions they can. But it's going to be a batten down the hatches sort of weekend for them. Friday and Saturday will be devastating. I wanted to say, but I'm not going to, talk a little bit about Hermine. One of the interesting things, and maybe we can do this next week. One of the interesting things about the forecast of Hermine is that it turns into a really impressive storm. And it's coincident, again, we're going to have a really cold week here this week. And I wanted to show that in the forecast. You can look at it on your own. Relatively cold. But it's going to, Hermine, when it gets to Fort Myers, is going to interact with a cold front that is a pretty impressive one, quite as impressive as this one that we just saw this week. The problem is, I think, is that there's no particularly strong upper support for that feature from the mid-latitudes, and the interception of the hurricane with the mid-latitude structure is well too far south to allow the same kind of interaction. That's a working hypothesis. Hermine kind of dies in the Atlantic as it gradually makes its way across the state of Florida. It's going to really get hammered. And but it does not have any of this redevelopment that we've seen in the last 2 weeks. And I think that's a function of where the interception occurs, as well as what the dynamics of the extratropical contribution is when the intercept occurs. So I wanted to show you one more thing, and it's not with relation to any of this. It's the PDF, Pete, if we can find it. We had it on the desktop, so I don't know if that's where it is now. But anyway, the 850 millibar cold pool. On the 12th of September, we were running the 3rd warmest September of all time in the Northern Hemisphere by this measure. I look at where the -5 isotherm is at 850 and calculate the area every day. Now we're down to the 11th warmest. So we've had a pretty cold, a chill week, if you want to talk about it the way you young people do. We had a relatively chill week, and I can show you how it's looking compared to the to the average. Posha's having a blast right now in her head. But we actually did, so I'm telling you the truth. I'm not making things up. Yeah, there it is. Thanks, Pete. Okay, so here's our map. So the gray lines, they're a little bit garish, unfortunately. The translation's not so good. But the gray lines are the range for every single day, September 1st to December 30th, over the course of 75 years in the analysis. And then 3 different averages. They don't depart much. This is this year's time series. So we're kind of coming right up to the average after having the warmest September 6th of all time in the hemisphere. But the warm days seem to be behind us. If North America has anything to say about it, we're not going to stay warm on average, because we're going to have a pretty chilly week in the eastern third of North America until about Friday next week. And that's when we'll get back together and talk about Hermine and its inability to convert because the system that it intercepts is too weak. So any comments or questions? Ian?
I was going to ask if we could see the Viz 5D again. I have a feeling the green parcels take a remarkably different path in the, once once they get to the same isobaric level, there should be difluent flow there. The green ones curl around and the yellows and oranges should curl to the right anticyclonically. I would expect, but I'm looking to see.
It depends on where they end up, because at every level, there's a different placement of the deformation zone or something that you might be expecting in the downstream of an upper low. So one has to pick that apart a little bit at a time. It's hard to make a broad statement looking at just the trajectory, as it animates. But you're right, that is true. And you can, when you're really careful about it, you can bisect a group of trajectories into those that will turn anticyclonically and those that will turn cyclonically. And when you do it, sometimes you find one of them sinks and one of them rises, and that makes it even more interesting than just the horizontal bifurcation. But see, the green ones get caught in the circulation of this whole big beast as well, and then they kind of go up over the downstream ridge, which itself is extraordinary. And all of the air gets down into that downstream ridge. It gets homogenized into that. So I don't know if this answers your question.
Can we also look at the upper level jet on this 5D?
Oh yeah, I have it already saved at like 60 meter per second, the isosurface. So I just gotta animate it maybe. So that's the upper front part of the jet, and there isn't anything yet of substantial outflow jet from Fiona, so here it goes. And then watch how this thing gets accentuated. Boom, that's where Fiona's really pouring outflow out as it redevelops. And that's where the jet goes. It's kind of cresting the big ridge that's over the North Atlantic. That's going to set up a sort of a North Atlantic block, actually, which may take a while to dislodge. So that's 60 meter per second. And if you tilt it up, you can kind of see where it is in the vertical. And it's kind of a sheet when it comes around the side of the hurricane, like right there. But you can see it blow up. The volume of it gets huge because so much air is being exhausted out of Fiona. I'm tilting the tropopause there. So. Any other comments or questions? Yeah.
I'm wondering, like, since we're going, we're in the shoulder season going into winter time, I think there's a difference between fall and spring cutoff lows and whether or not they get reabsorbed.
Oh, absolutely.
This one cuts off, you clearly have the PV change sign so that you've broken the Rossby wave, but it just gets, all the parcels go right back into the jet.
The difference, I think, the primary difference between the spring and fall is the presence of tropical cyclones in the fall. Everything's different about the fall transition circulation, I think, because of that. And this may be one of the manifestations of that difference. Because in the spring, when you lose a cutoff disturbance, I won't say evaporates because it gives the wrong context in a room full of physical scientists, but it disappears by radiative cooling, warming. If you shunt it to the south, it is gone forever. It will never be seen again. If you have a cutoff low in the autumn, it may well become part of a new redevelopment from something emerging out of the tropics, which doesn't happen in the spring. So that's a big difference.
Does spring also have polar night jet? Just asking for it.
The polar night jet exists at the beginning of the spring, but it's decaying. And right now it's trying to spin up. She already left. I had a great conversation this morning with Andrea Lang, who's an expert on this stuff. If you're interested in this, you've got to go talk to her. She's up in 1531. And one of the things that's different, of course, in the fall, and she's going to tell us about this in November, about cold air outbreaks. In the fall, there is no polar night jet until about middle of October. It's kind of getting spin up right now. And so it's easier for wave activity to be reflected at low elevation. In the wintertime, the polar night jet is really strong, and you have to go all the way to that height or maybe just above it to reflect wave energy. So it takes longer for the wave energy that might be initiated or instigated by a big cyclone in the Gulf of Alaska in January to actually have a downstream in time and space consequence in 2 weeks or 3 weeks downstream. In October or September, October, or early November, it might be only 10 days. Big difference. So it's really, really interesting. That's another substantial difference between the two shoulder seasons, is the presence and spinning up, but most absence of the polar night jet. It's so interesting, these different connections. And I think, I've been in the field a long time. It seems to me people who think about weather systems 30 years ago never thought about those various connections, not even the tropical transition problem. And so it's a brave new world. I mean, all the ways that you have to think about it's truly synoptic. You've got to think about everything, not only at the same time, but at all multiple different levels and different types of processes to really have the most comprehensive view of how individual weather systems live their lives. And if you don't do that, then, well, I should say it in the more positive way, if you do that, and I hope we're helping to inculcate that as a perspective here in this department, if you do that, you're in the best position to make the best sense out of the weather and climate interface. Because right now, still, weather scientists and climate scientists have a little bit of difficulty talking to each other. Less than they did 25 years ago, but still some difficulty. It's a different vernacular. It's not because they're snobs. It's a different vernacular. It's a different perspective. It's all that. So anytime you're invited to one of those conversations, go and fully participate. Don't expect you're going to be disrespected because you're a weather person if you are. That's not what I mean. It's just that you have a different vernacular, a different way of thinking about things. But the more that we can think about as many different physical processes on as many scales in time and space as possible, the better prepared we are to make those connections with those scientists. Because they got a lot to say, but they also have a lot to learn. So, just like we do. All right, I'm off my soapbox. Any other questions? Can't help it sometimes. Okay, thanks everybody. Thank you again, Pete. Look at how Pete drives through all of this stuff, and I'm going like this, and he just doesn't miss a beat. It's fantastic. Thanks very much for being here. I mean, thanks.
Where are you going?
I don't know.
All right, come to the student lounge.
You want to go to the library?
Yeah, actually, that's a good great idea. AOS library?
I was thinking the library.
Which library?
Oh!